research about sensor, I need to worry more parameter. However, I have to get on time, so I just focus on the most important. However, there's something here. Focus on the first thing you would like to ask. I have here HPLC and three electrochemical sensor, but have different recognizing material, biomaterial, nanomaterial, and NIP. And this is my work. And about the working range, the winner is biomaterial. It can, at least in the in this case, it's just about the detection of antibiotic inside water. It can measure something in femtomolar. The second winner is HPLC. It starts from picomolar. And the next one is my work. From my work here, it can detect something from 1 nanomolar to around 40 micromolar. But at least it's better than nanomaterial, because this material lack of some selectivity. It can detect something from 100 nano to 200 micro. So the winning is biomaterial, and then the second is HPLC, and this material is the tusk.
So what can you say about, let's say, what are the advantages of the system then? Which points here are the most important one then?
The most important is that it can mimic the recognizing of material. It may not reach this value, maybe not yet. It's still in developed concept. It's still continue, but at least it's more selective than nanomaterials. It's just talking about linear and the working range of the sensor.
But even if, let's say, if you take this allowed concentration of these microorganisms, so let's say this antibiotics, I don't know exactly what are the allowed concentration levels in natural water.
This depends on the standard. For example, like antibiotic, as I understand, it can present in very low to very sometimes
But can you quantify, let's say?
quantify.
Yeah, because we are chemists, you see, we don't see that it's high or low, but what are the numbers?
From the paper that's confirmed that some problems start to happen, it can be from around pico to nanomolar. So far,
Something around picomolar.
yes,
So that's
picomolar.
quite a long way to go until you reach this limited detection
Yes.
of the sensor.
Yes.
Yeah. Because usually, these are very low concentrations, and it's quite tricky to reach these allowed levels.
Yes, not yet with
Yeah, sure. Yeah, but I just wanted to ask you.
Yeah.
And then regarding the selectivity, you see, you didn't point out it here. What about the selectivity, let's say, of this HPLC and your sensor?
The winning also HPLC, I'm afraid, because selectivity.
Well, I say you have a mixture of different compounds, because in natural samples you have this. You don't know in advance what there are. Then what can you say?
My current sensor cannot measure that, unluckily. I would like to ask again to understand your question clearly. For example, I have one sample, have both ampicillin and something else. Why my sensor respond like this for the target? If in the sample have both of them, it may respond higher. How can I know how much exactly for the target? Is it what you are doing?
Yeah, exactly.
Current sensor I cannot measure it exactly, but the idea is coming up. For example, some solutions like maybe the simplest one is maybe some cut-off level. I'm not sure. But the second more practical I saw is in an article is about combine more than one sensor. For example, like one array sensor, and understand the pattern of the data, and using some analytical method like PCA, principal component analysis, or even some later on after machine learning start to become a thing from 2019. There is tool, as I remember, they also use the machine learning to understand the array of the sensor data. recurrent. My sensor cannot measure exactly. It can just give the higher response toward the target they order.
So you have ideas how to go further.
Yes, yes,
Fine.
yes.
Fine. Then regarding the price, I just wanted to specify. You showed here like 2 kilos and 200 kilos. Does it mean the equipment price, or let's say, can you also evaluate the price for one analysis? Maybe?
It's very difficult because as a student, I don't know about the price. It also depends if, I guess if my supervisor buy 2 box, it will different price from 50 box, and also need to calculate the money for people working on it. So the price here is just about equipment. It can be from, as I saw on the Google, it can be from 50 to 400 something. So this is the average price for the machine only. And this is the price for the potential start to measure the signal from electrochemical sensor. But how much for one sensor, how much for material, how much for people working, I really cannot estimate. But in general, biomaterial is supposed to be more expensive than some monomer. And again, it can be, if have to say the number, I can say around 5 to 20 euro for each chip. But this is very depends.
And I also noted that you mentioned that lifetime is 1 and 1,000. So 1 doesn't mean a single use sensor, or?
Yes, I mean that single. For example, HPLC is easy understand because it's a column. If careful can reach to 1,000 time use. But in case of all of these sensors, I'm afraid that it's just one time use. If I want to use it again, I need to some process to remove the target from the sensor and then can reuse it again. So I have given one line about reusability or more specific regenerations. The column of course only one time. If calculate this one 1,000, I saw into article the biomaterial can one article say it should not be reused, but the second article say it can be 5 times. This is about my work. I didn't measure it, but exactly in my work for each value, I will give one sensor, measure, regenerate, use again, regenerate, use again, so total 3 times. And based on the experience of our lab member, we can up to 12 times. And see, I cannot find the exact data for nanomaterial, but I think it's similar to this somehow about synthesis material. It's not so much selectivity volume, so it can be used at least more than this number, around more than this number.
Because based on this reusability, I was wondering, because you stated here many times that it's very cheap, your sensor. But if you consider also the reusability, then it's not so cheap. Let's say if you calculate the price for one analysis.
Yeah, why I say for one.
But it's okay.
Yeah.
Mm-hmm. So we'll discuss this. Yes, let's go to the sensor itself now, because it's the most interesting part, I think, of your work. So what are the main challenges of preparing lips, and what are the artificially recognizing compounds from pollutants we know?
The most difficult part for me, I think, and for the meat community, I think is what monomer is the best, because it's not only effect to the recognizing capability, but it also affect to the stability of the material and everything. We have a huge amount of monomer, but only a limit amount that can do synthesis by this method. So among all of those suitable monomer, which one can form the strong bond to work here? And also, it's good that it can be bond strong, but I also it's not too strong because later I need to remove it from here by the removal process. And also, if they just manually do, there will be a lot of things to do. There will be computational approach to limit the amount of practical work. However, the computational thing is not perfect. there's many things like even quantum chemistry consider the condensity of the electron, everything, but it can be very good number, but not so sure until we do the practical thing, can see the imprinting behavior here. So it's the most problematic for me for the process of design of the sensor.
And that was also a question for me either. When you just focus on this, let's say, group specific bits. And you also showed these different monochromate lights, yes? But the structure is quite different, you see. And I'm not sure that it's okay just to use the same bit for the same, all these three structures. So what do you think? Can you comment? Because if you look on these lacton rings, you see, we go now in very deep chemistry. You see, you have a 14-member lacton ring, and then for this tetrabutene, you have 15-member. It's totally different actually, and you focus on this hydrogen bonding, yes, mostly. And also in these positions 11 and 12, you have this deoxide, so they are somehow structured differently. Can you comment on this? Because this nitrogen in this lacton ring gives very specific interaction with this mix matrix.
Absolutely correct. Yeah, what you say here, completely correct. But however, I want to say here, at least in the three target here, I have this diode. So the diode, the ring can be different from here, like this root different from here. So the first thing I can say that maybe the bonding between the boronic acid to work here can be weaker, stronger because of this, but it still present here. The next thing is that the ring here also different with the resonance of nitrogen and also the OH in different side of the molecule. But I understand here only one group, it still can form the bond to boronic acid. And more important in imprinting, I'm not worried the single oxygens or single dione itself, but I take care here is the so-called shape, the size, and there's so many other positions to bond. I working here to focus on the ring, but actually, at least in these three cases, all of this component around here also similar. That's why my sensor, I think that it can detect all of them, and the result really prove it.
Because why I'm asking this, because if you look at your results and the sensor signals for these different three antibiotics, actually the response is different. That's why I'm asking, because it indicates somehow that the interaction between this anabatic analyte and this liquid are different.
Yes, this can be different, can clearly see here. But if in this, can see that it has some difference, but it's not much. Of course, I cannot confirm exactly number. It has to be more or less, but cannot deny it. It has some difference if the sensor responds to three different targets. And this is in the case I'm working with three members, but maybe all the other members they may have some difference. So, but I think that based on the whole structure, it can be, for example, it can give some reason here, I don't know, I need to test it, but it cannot just disappear. Since it's shown here very clear that it's the real reason, so that it can somehow be kind of similar reasons.
You already showed this. Can you tell me what is the signal at the zero concentration of the sensor on the calibration point? Because it doesn't cross the zero point here.
Yes, it doesn't, because
This
this
is some physical meaning of this signal.
this can be, because in this case I use here in BPS, maybe it's in real life. If talking about theory, of course, if no concentration is supposed to reach zero, but in real life in BPS, it's also can some component It can modify, or it just like the surface when read DPS is supposed to have something, some reasons. So very depends that sometimes I fix it just a little bit discuss beyond your questions. Sometimes I can fix the weight at zero, like in the first work or in the last work, but in this work I just let the weight there.
Okay, but you acted differently in the case of Sicily. I think on your slide 17, I think, this calibration protocol is called.
Yeah.
What can be the reason of different mix then? Because we are discussing about the preparation or production mix.
Yes.
It should be some reason coming from mix. Do you have any ideas what can it be?
Sorry, I don't exactly understand your question. With the
You see, this calibration clock goes through this 0, 0 point.
yes,
The other one not.
yes. I think it just in reality, it's never reach zero. There must be something. I guess it can come from the component of the DPS itself.
Can it be also the reason of this choice of selection of polymers? Maybe different polymers can act differently?
It can be possible. If I chose a different monomer, I can see it different. But maybe the reason I chose the monomer here is fully based on the combination between our theory and the quantum chemistry calculation, how strong the bond here is sample. For example, in this case of ampicillin, aniline, if I combine, I calculate the strength H of propycin, I combine them, aniline give the highest energy. So I just start from there. Maybe some different monomer is better.
Yeah, it can be the reason. Yes, but let's go back to this cavities of your mix. Let's say this specific cavities.
Yeah.
How big are they? What are the dimensions?
I don't know in reality because I can see it in this picture will be bigger. I can see it by computational approach only. I have here is, for example, ampicillin. This is bent like this. This is the molecule of a monomer, and if based on this, this will already optimized by universal phosphate, and the size between here to here, the last molecule is about 1 nanometer. From here to here also about 1. So I guess the cavity around about 1 nanometer.
Or maybe any.
Yeah, that can be more, can be less, and I am not sure any thickness can measure it correctly.
But at least the range of the dimensions is in this nanometer scale.
Yes, based on
It's
the
around less than 5 nanometers, let's say.
yes, yes.
And then you just optimize also the thickness of these lip layers on your sender. And there you found that the optimal thickness is 12
Yes.
nanometers. How many, let's say, levels of different cavities can be placed within this lip layer? Or are there different, let's say, layers of these cavities? Or are they only on the surface?
It's not only on the surface, as I understand, it's also inside, under the surface, it's also inside. But exactly how many layers we can measure or estimate by computation.
Because I know from the literature that actually usually they consider that the big thicker layers are better because they also, the inside cavities also work, and they give, let's say, this broader in different ranges. But you found that it is almost 50 times smaller than described in the literature. Can you comment somehow?
Yes, of course. This is in the second research. I find out that the optimal result is 12 nanometer. You're absolutely correct. When the thicker, maybe more the possibility, more amount of the binding size. However, it very depends on what kind of monomer. Because I'm new here is NPD, and in literature, they already researched to show that it reached around 20 nanometer, the 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 the, the electrochemical activity may not observe anymore. So even with my techniques, I cannot make the polymer thicker than that. It's the first thing. And if that thick around 20 nanometer, it can fully block the signal. I cannot observe the signal anymore. And also the different, just beyond your questions, the different problem is maybe some material at thick at good, but it also bring problem for washing our process, because it may not like in my case I just need 15 to 30 minutes to remove the template. However, in some research they make it thick, like you say 200 nanometer or more. It may need 12 hours, 24 hours.
But have you also watched this, let's say, the number of these cavities from the other side? You see, you know how much template molecule you use. And probably you know also this, let's say, the surface of this lip. Do you?
No, I didn't measure it.
Because actually it can be possible, you see.
Yes, it may possible, but to be honest, I just think I haven't measured, but I also think that it may be not possible, because the first reason is the film very thin, and it may be difficult to measure because the noise of the signal and the thickness maybe is not cannot measure. I'm not sure about this, but in general it's kind of difficult. Even the thickness I'm using here is ellipsometry. It's the very good technique, but also we also face a lot of problem to measure the thickness. We need to be exactly, because the surface is not homogeneous. It's not equal everywhere. Somewhere maybe more porosity, somewhere maybe less. So we need to measure the bone and then keep it there and then form the polymer and proceed and measure again after that, right exactly that part. So a lot of noise from the base, from the solution maybe interfere, but it's correct that maybe it's possible to measure the concentrations of the template and somehow estimate the amount.
And you mentioned that ellipsometry here, yes?
Yeah.
And we use this technique for this, let's say, evaluation of this washed out matrix compound, yes?
Yes.
To be sure that there is no remains. Did you also somehow quantify, let's say, this washed out matrix material analytically? Because I was wondering, you have a very good sensor, you use this matrix template. Why didn't you use your sensor just to evaluate the amount of matrix material which is washed out?
I didn't do it. I use here beside the ellipsometry to confirm that the template removed. I use also some other technique easier to see, like here in my case in all the work I use CV and ACE impedance spectroscopy. It cannot measure exactly the concentration, but it gives me the idea that the concentration is removed from the structure. And as I understand, for my work is more important about the rewriting result in the end. Maybe it's interesting to quantify that concentration was removed from the template, but again, I need to try, and I'm afraid that the film that it is with all the noise and everything, I'm not sure, but it can be tried.
Can you comment, what is the limit of detection for this ellipsometry?
based on the graph, I can confirm that it's removed. But based on what I have here, I cannot confirm 100% the template was removed. But I can here, I cannot confirm here 100%. But about the one thing about the optimization of the washing out time, I didn't look here, but in the previous work of our group, it's I could draw here. So for example, like after 5-10 minutes and so on, and around 30 minutes, we observe that it's nearly stable here. So maybe I estimate around 30 minutes, at least in similar in my case about MPD, around this time is nearly all the isosceles back then the template that possible to remove by my method will already remove, but I cannot confirm 100% only.
But the plateau actually depends on the porosity and also the thickness of
Yes, it depends, but in why all my case here working with poly LED, so I guess the thickness should be not much different. So it's around this time. For the first few steps, of course, I try 45 minutes and something, but around this time, I really don't observe any much different. So it's also more benefit for the research process.
the production of this mix. You use this micromolar concentration of this matrix, yes?
Sorry, but
This if you produce your mix,
yes,
the matrix material was in micromolar concentration. Millimolar, yes. And your, let's say, the detection range is in nanomolar, micromolar.
sorry, not yet. I understand your question. You mean during the
If
process?
let's say, if we compare the concentrations of
Yes.
your matrix material, because these just form the cavities,
Yes.
and the cavities are used for the detection of different analytes. And the analytes were analyzed in the range of, let's say, nanomolar and micromolar range.
Yes.
So it's 1,000 times lower and 1,000,000 times lower concentration. Yes.
Compared to the concentration at the depth.
This compared to this matrix concentration.
Okay. Sorry, I just write out about the template concentration.
When you prepare your
Okay. Okay. Okay.
it was in millimolar. And then you do your mix, the detection of micromolar. Do you have any ideas? Do the mix also work on very, very low concentrations and how this mechanism is on that? Yeah, it's a very, very difficult question, I know.
Yeah.
Do you have some ideas?
Yes, I think I can try from some idea logic how to answer. The first thing, the first reason I think that not all of the template here was removed during the process. Maybe like you say, it's cavity from the surface, but a lot of templates will be under here, under the surface, can remove by my method. The second is that also that the surface, the measure signal between the meat with my sense can user system, and the meat itself is not homogeneous. It's will be somewhere more affinity to the target. It's somewhere will be less. So in the low concentration, it will try to run into the high affinity first, and my potential start here can measure something from picoampere, very small. So as long as it can detect the signal, distinguish it from the noise, so the system can measure something around there. So maybe it's some logic to start to find out the answer that how my sensor can measure something very small.
Because what I remember